Assalamualaikum, one and all. Today's episode is about centripetal force. How is this concept applied to a body in uniform circular motion? And how is it applied to a situation like bunking of curved roads? To find out, just stick around till the end of this video. Watch and learn. Question number 1. A small remote-controlled car with mass 1.60 kg moves at a constant speed of 12.0 meters per second in a track formed by a vertical circle inside a hollow metal cylinder that has a radius of 5.00 meter. What is the magnitude of the normal force exerted on the car by the walls of the cylinder at point A, or the bottom of the track, and letter B, at point B, or the top of the track? Identifying the given data, we have the mass, small letter m, of a remote-controlled car equal to 1.60 kilogram. It is moving at a constant tangential speed denoted by v sub ton equal to 12.0 meters per second in a track formed by a vertical circle inside a hollow metal cylinder that has a radius r equals 5.00 meters as shown in the figure. We represent this constant tangential velocity with a blue arrow, right? And labeled v sub ton. So at point A, the direction of this tangential velocity is to the right, while at point B, its direction is to the left, which suggests that the toy car is moving, all right, in a counterclockwise direction along the track. All right. So we are asked to find the magnitude of the normal force, denoted here by F sub NA, at, for letter A, at point A. All right. And this normal force exerted by the track on the toy car is directed upward, denoted here by F sub N, A, and represented by the red arrow. While at point B, the direction of the normal force, all right, is downward. And it's also labeled as F sub NB. And at each point, A or B, we also consider the direction of the car's weight, all right, mg. But for simplicity, all right, the weight of the toy car is not anymore represented in the diagram, all right? But let it be understood that the direction of the weight of the toy car is always downward, all right? So that means at point A, the direction of the weight is opposite to the normal force, while at point B, the weight of the toy car is in the same direction as the normal force F sub NB. All right? Now, um, in solving for the normal force at point A, all right, we're going to derive the equation for the normal force based on the concept of uh, Newton's second law of motion, all right, which states that the direction of the net force is in the same direction as the acceleration, all right. So at point A, we say that the net force acting on the toy car, okay, is towards the center of the circular track, all right? And mathematically, we can label this net force as the sum or vector sum of the normal force F sub NA and the gravitational force on the toy car, also known as the weight of the toy car. So the magnitude, all right, of this net force can be expressed in this equation. F sub NA, understood to be positive or directed upward, minus the weight mg, and that is equated to mv squared over r. Well, where mv squared over r is understood to be the centripetal force. All right? The centripetal force that provides or that makes the toy car move in a circular path. So that centripetal force, of course, is also directed upward or towards the center of the circular path. So, if you are going to transpose this equation, we will come up with the working formula for finding the normal force F sub NA. All right? So we just transpose the weight mg to the right side of the equation. So it will become mg plus mb squared over r, or factoring out the mass m. All right? We now have this working equation for finding the normal force at point A. That is, F sub NA is just equal to the mass of the toy car times the quantity square of the tangential speed, all right, that is denoted by v tan squared, divided by the radius of the circular path plus acceleration due to gravity, small g. Now, at point B, all right, we also have the same equation, all right? It's just that this time, the direction of the net force or the centripetal force, all right, is that it is directed towards the center of the circular path. That means F sub NA and the centripetal force are both directed downward. Hence, the negative sign in this equation. All right? So, the net force, which is the vector sum of the uh, what we call normal force at point B, F sub NB, all right, and the weight, all right. Since both are directed downward, so they're also with negative sign. And that's also true for the centripetal force. There is also a negative sign, negative mb squared or v tan squared divided by r. And when we transpose, all right, and isolate the normal force F sub nb, we come up with this equation. F sub nb is equal to the product of the mass times, all right, the square of the tangential speed or v tan squared minus acceleration due to gravity. So, based on these two equations, we can actually predict, all right, that the normal force at point A will have a greater magnitude compared to the normal force at point B. Can you guess why it is so? Executing our formulas for letter A, finding the normal force at point A, all right, using this equation, we have the mass of the toy car 1.60 kilogram times the square of the tangential speed 12.0 meter per second, that's to be squared, divided by the radius of the circular path 5.00 meters, all right, plus acceleration due to gravity or 9.80 meters per second squared. So when we do our math, we get the value of the normal force F sub NA equals 61.8 newtons in three significant figures. Now, for letter B, finding the normal force F sub NB, all right, using this second formula. So, we get, okay, the mass, which is 1.60 kilogram multiplied by 12.0 meter per second squared divided by the radius, all right, 5.00 meters, then minus, so this time it is minus 9.80 meters per second squared. So again, simplifying, we get the normal force at point B equal to 30.4 newtons, also in three significant figures. So these computed values for the normal force or forces, they both agree with our earlier predictions, all right, that the normal force at point A, okay, will be greater than the normal force at point B. So actually, intuitively, the normal force at point A must be greater than the normal force at point B, because at point A, the walls of the cylinder have to exert a harder force because of the toy car's downward weight, seemingly pressing on the walls. Whereas at point B, the walls of the track are not uh, pressed by the weight because the direction of the weight is also downward. All right. Hence, its contact force on the toy car is minimal. Our last question, number 2. A racetrack curve has radius 90.0 meters and is banked at an angle of 18.0 degrees. The coefficient of static friction between the tires and the roadway is 0.400. A race car with mass 1,200 kg rounds the curve with the maximum speed to avoid skidding. Question letter A. As the car rounds the curve, what is the normal force exerted on it by the road? Question letter B. What are the car's radial acceleration? And letter C. Tangential speed. The racetrack curve has a radius of 90.0 meters and the banking angle theta is 18.0 degrees. The coefficient of static friction, denoted by mu s, is equal to 0.400. The race car with a mass m equals 1,200 kilograms rounds the curve with the maximum tangential speed to avoid skidding. And the target variables are letter A, the normal force F sub n exerted by the road on the car as it rounds the curve. Letter B, the radial acceleration denoted by A sub r, also known as the centripetal acceleration. And letter C, we are also asked to find the tangential speed of the car. So before we proceed to our computations, let us identify and emphasize the forces acting on the race car. Okay, we have number 1, F sub n, or the normal force exerted by the roadway on the car. All right, and as the word normal force suggests, it is the contact force exerted by the road on the car perpendicular to the surface of the road. And that is labeled here or represented here by the red arrow. Next. All right. This normal force is broken down into its x component. All right. The x component, all right, is expressed here as the normal force multiplied by sine of the angle theta. All right. And its y component directed, of course, along the positive y-axis and is expressed here as f sub n times cosine of the angle theta. Of course, we have the weight mg, the weight of the car directed downward or into the negative y-axis. And the other important force given is the static friction, denoted here by F sub s. All right? And this static friction is what prevents the car from skidding? All right. And based in our drawing, this static friction also has its x and the y components. All right. For the y component, uh, the y component of the static friction is directed downward or along the negative y-axis, and it is expressed here as f sub s multiplied by sine of the angle theta. And its x component, all right, the x component of the static friction is directed along the negative x-axis, all right, and it is expressed here as f sub s, or static friction, multiplied by the cosine of the angle theta. All right. We are also emphasizing that the centripetal force that makes the car move around the circular curve, all right, we denote that by f sub c. It is in fact the sum of uh, the what we call x component of the normal force, all right, which is f sub n sine theta, and the x component of the static friction, all right, expressed as f sub s cosine theta. So we may say also that this centripetal force is the net force acting on the car, which gives it, all right, a centripetal acceleration, all right, denoted here by this formula. Radial acceleration or centripetal acceleration equals the square of its tangential speed divided by its the radius of the circular path. For us to be able to find the normal force, we consider the static equilibrium equation along the y-axis. That is, the summation of Fy must be equal to 0. All right, which means that the upward force Fn cosine theta, all right, is equal to the downward forces mg plus Fs sine theta. All right, where Fs in this equation is the static friction equal to the product of the coefficient mu s and the normal force F sub n. So transposing uh, this mu sub s times F normal to the left side of the equation and factoring out the normal force, we get its working formula. All right? The working formula for F normal is just equal to the weight mg divided by cosine of the angle theta minus the product of the coefficient of static friction mu s multiplied by the sine of the angle theta. For question letter B, in computing the radial acceleration a sub r, we just apply Newton's second law of motion, where the radial acceleration ar is just equal to the centripetal force, Fc, divided by the mass of the car, where the centripetal force Fc, all right, is also the sum of the static friction F cosine theta plus the normal force multiplied by sine of the angle theta all over the mass m. And lastly, for the tangential speed v sub tan, we just get the square root of the product of the radial acceleration and the radius of the circular path, small letter r. All right, so executing our working equations for letter A, finding the normal force F sub n, we have the mass multiplied by g, or 1.20 times 10 to the third power kilogram times 9.80 meters per second squared, right? And their product will be divided by uh, the value of cosine of the angle theta, which is cosine 18.0 degrees, all right, which is 0.951 to 3 significant figures, minus uh, the coefficient of static friction 0.400 times the value of the sine of the angle theta, or sine 18 degrees, 0.309. So once again, doing our math, we will arrive at the value of the normal force F sub n equal to 1.42 times 10 to the fourth power Newton, also in 3 significant figures. So moving on to question letter B, the radial acceleration using this formula. But before that, we have to find first the value or magnitude of the static friction F sub s. All right? Multiplying the coefficient of static friction 0.400 by the normal force that we just computed, 1.42 raised to the fourth power Newton. And that is static friction equals 5,680 newtons. So this value of F sub s will be used in our calculation for the radial acceleration. That is, multiplying this static friction 5,680 newtons by the value of cosine of the angle theta, which is 0.951, that will give us 5,402 newtons. Likewise, multiplying the magnitude of the normal force 1.42 times 10 to the fourth power Newton by the sine value of the angle theta, all right, equal to 0.309, what we get is 4,390 newtons. So the sum will be divided by the mass of the car, 1.20 times 10 to the third power kilogram. So finally, simplifying, we get the value of the radial acceleration equal to 8.16 meters per second squared, also in 3 significant figures. And last but not the least, computing the tangential speed of the car using this formula. V tan equals square root of the product of the radial acceleration and the radius of the circular path, substituting square root of 8.16 meter per second squared times 90.0 meters. Doing our math, we arrive at the value of the tangential speed equal to 27.1 meters per second, also in three significant figures. So this is the speed of the car, or the required speed of the car, so that the car, all right, will be able to maneuver perfectly around the circular curved path without skidding. And that ends our tutorial for this topic. Till the next episode. Mabuhay. Masya Allah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.